Hi everyone, welcome to our channel Learn Competitive Programming with CodeChef. If you are interested in competitive programming and want to learn and master data structures and algorithms, then this is a one-stop destination for you. Every week, we'll post CodeChef problem explanations, conceptual videos on various programming paradigms, and also conduct live problem-solving sessions. But before we get started, here's a reminder to hit the subscribe button if you haven't yet already. Great. Now that you have subscribed, let's get started. Today we'll be solving the problem the WAV, which is a simple problem and it belongs to the June Cook-Off. So let us go to the problem statement. The problem statement here says that we are given a polynomial here. This is our polynomial and we are given the roots of the polynomial which are distinct. So each root is distinct from the other one and the roots A1, A2 up to AN. These are the roots of the polynomial. So they are denoted by AI. In this polynomial, this is the root and we are given. And they are not given in any order like increasing order or decreasing order. They are given randomly to us. Now we will be given few number of queries. And in the query what we'll have a single integer x, which says that we have to find out that by using this x in this polynomial, what will be the sign of this polynomial, whether it will be positive, it will be negative, or it will be 0. So basically what you need to find in the question is that if we will be given some few number of values of x, and for each query you will have to find out whether p of x is 0, it is negative, or it is positive. So this is our problem statement. Now let us see that how this polynomial can be expanded in order to deduce a plausible way in which we can find out that what sign it will give at the end. So if we expand this polynomial, then it will produce the terms x minus a1 into x minus a2 into so on and x minus an, because you can see I equals to 1 up to n. So there are n terms in a polynomial. And this sign that you see here, this means product. So each term of the polynomial will be multiplied. Now one thing we can be sure of is that each term of the polynomial will contribute to the final sign or the final answer that this polynomial will give. And we know that a1, a2 up to an, these are the roots of the polynomial, so they are already given to us, and x will be the queried value. So how do we know that it will be a positive, negative, or 0, the answer of individual term? So that is very easy, right? If x is less than ai, if the queried value is less than the root, then this term will give us a negative answer. If the queried value is greater than the root or the ai, a1, a2 that is used, so then x minus ai or the individual term will be positive. And if x is equals to ai, in that case the term will result in 0. That is what I am talking about, the individual terms of the polynomial. Now these two we will talk about afterwards. Let us see the third condition. So in third condition it is that if the root and the queried value is equal, then the term will be 0. Now what this means? It means that x is the root itself. X is one of the roots of the polynomial that are given to us. So directly we can say that if the queried value is one of the roots of the polynomial a1 up to an, any root, then in that case the individual term somewhere in the polynomial will definitely be 0. And if one term of the polynomial is 0, then this entire polynomial will result in a 0, because here we are multiplying the terms, and in multiplication if any one term is 0, then the entire expression or the entire result will be 0. So one thing we have deduced, that if the queried value is equal to any of the roots of polynomial, then p of x will definitely be equal to 0. Now we have to find out about the positive and negative sign. Now in multiplication of signs, if there are two negative signs to be multiplied, then it will result in a positive value. If there are one negative and one positive sign to be multiplied, then it will give us a negative value. And if both are positive, both the signs are positive, then it will give us a positive value. So you can see that if there is one term which is negative, then it is giving a negative value. So it is determined that if one term is negative, then it will give us a negative value. Now what about two terms? If two terms are negative, then it is giving us a positive value, right? Now what about three terms? Now if three terms are negative, then again two terms will result in a value positive, and the third term, which is negative, will again be multiplied with the positive term, so then it will result in a value negative. So again, if there are three terms which are negative, then we will get a negative answer, means a negative sign. Similarly, if we have four terms which are negative, then we will get a positive answer. Now what do we see in this? What is the pattern that we see? That if the number of negative terms are odd in number, then in that case the polynomial will result in a negative sign, means the result of the polynomial will be negative. And if the number of negative terms are even in number, then the result of the polynomial will be positive. And how so? Because each of the two negative terms, because they are even in number, right? When they are even in number, so two negatives will form a positive. So there will be no extra term which is negative there. That is why it will remain positive. And if there are odd number of negative terms, then at last one negative term will be left. So that is why the entire answer will also be negative. Now, how do we know that how many terms in the polynomial will be negative? So there is a very easy way of doing that. We know that a term will only be negative if x is less than a of I. It means that if the queried value is less than the root, then our term will be negative. So if we just find out that how many number of roots are greater than the queried value x, then we will be able to know that how many terms will be negative. So the number of roots which are greater than the queried value x, this number of roots will give us the number of negative terms that we'll have in the polynomial. So again, we have deduced that if this number c, where c is the number of roots which are greater than the queried value x. So if this c is odd, then in that case the polynomial will result in a negative sign, and if this c is even, then the polynomial will result in a positive sign. So guys, this is the entire explanation of how this problem has to be solved. Now we will see the implementation part, that whatever we have discussed, whatever explanation we have discussed, how can we implement them? So there are various methods to do this implementation. Let us discuss that. In method 1 of the problem solution, first we are required to sort the roots in increasing order. Now why we are sorting the roots? Because we will be using binary search in order to determine that how many roots are greater than the queried value x. And how are we going to do that? So binary search lets us find a position in the array, and this position tells us that whatever our value was, in this case which is x, whatever our queried value was, so from this position in the array, all the values left to this position will be less than x, and all the values right to this position will be greater than x. So if we can find this out, then we will be able to determine that how many roots are there in the array which are greater than the queried value x. And after we have found that out, so this number will let us determine whether the polynomial will be negative or it will be positive based on the number of values are even or they are odd. And if at this position the root is equal to the queried value, the root value is equal to the queried value, in that case the polynomial will have the value as 0. So this is one method of solving. And what will be the time complexity? So there are n number of roots which are given to us. So sorting the array of roots will take n into log n time complexity. And step 2, we are performing binary search on the sorted array. So binary search, it takes log n time complexity, and this we are performing for each query, right? So each query means the number of queries are q. So q into x will be the time complexity. Now, what will be the final time complexity of this method? So it is going to be n plus q into log n. So guys, this is one method by which you can solve your problem. If you do not know about binary search, then you can definitely go out on the internet and read about it, see how to do binary search, and then you will be able to understand how this method has to be implemented. Now we have another method with us which is a better approach to this problem. So we'll be discussing that and we'll be doing the code of that solution. Now to understand method 2, we will take the help of an example. So here first of all we'll sort the roots in descending order. So consider these the roots of the polynomial. There are 9 roots of the polynomial, so to see, and I have put the index values on each of the roots. So indexing starts from 0 in programming. That is why I have put the indexing from 0. Then we have taken the queried value x to be 3. And we'll have two elements, two terms, jump and position. Now what these two terms will do, we'll discuss about it. First, let us see the second step. So the second step says that after sorting the roots in descending order, we will find out the first position in that sorted array of roots such that the value of the root has become less than the queried value. So where can you find this value in this sorted array? So x is equal to 3. So you can find it at this position, at the 7th position. Now, when you have found this position out, then you will be able to determine one thing, that how many roots are there which are greater than this value x. So count the roots 1, 2, 3, 4, 5, 6 and 7. And this position that you have found out is 7 itself. So this position will let you determine how many roots are there which are greater than x. And using this position, you will be able to find out if the polynomial will be negative, it will be positive, or at this position, a of position, if it is equal to x, that means that this queried value that is given to us is a particular root of the polynomial. In that case, the polynomial will be 0. If this position is odd, then that means the polynomial will give us a negative sign. If this position is even, then the polynomial will give us a positive sign. But to find out this position, we will do some extra steps, and those extra steps will help us optimize our solution. So what those extra steps include is that we will take a jump value. Now this jump value will be the square root of n. So here n is equals to 9 because there are 9 roots of the polynomial that we have taken. So jump value will be 3 here, and position initially will start from 0, right? Now in each iteration, we will check whether this position plus jump is whether at this position a of position plus jump, whether this value is greater than x or not. If this particular value will come out to be greater than x, then again we will increment the position by position plus jump. So this way, what is happening? That we do not have to iterate through each of the values here. We do not have to iterate through each of the values in order to reach this position 7 that we have found as our answer. Instead, what we are doing, we are jumping 3 values at a time. And if we do that, then significantly the time complexity of our problem will reduce up to a very good extent. Now in the first iteration, this particular condition will be checked for this value, because position is 0 and jump is equal to 3. So 0 plus 3 will give us the third index. Then second time it will be checked for the sixth index. So both of these in both of these iterations, this condition will be true. So the position will be incremented by an increment of jump. So position right now will become 6. Now the next time when we'll do position plus jump, it will be 6 plus 3 equal to 9. Now 9 has gone beyond the number of indexes that we have, the number of indexes of the array. So that means definitely the condition will become false, because we will check one more condition, that position plus jump should be within the range that is given to us, within the number of roots. So then this value will become false. That is why it will stop here. So our position will become 6 after performing these two iterations. Now it has become 6. Now what does it say? That up till this position, the root was greater than x. Now if the root is smaller than x, then it will only be after this particular index 6. So instead of checking all the values, whether the first value is less than x, whether the second value is less than x or not, because what is the second step? The second step is to find out a value in the root which is less than x, the first value in the sorted array. So instead of checking for each and every value, we have reached a point where we know that after that it can be less than x, but before that we are sure that it is not less than x. So we'll have to check for lesser values, right? So now we will start checking from this particular value, from the 7th value. So here we will have to check for just a single value, and we will find out that which value of the root is there which is less than x, the first value of root in this sorted array, which is the 7th value. And this way we will also be able to find out that how many number of values of roots are there which will be greater than x. So which are 7 values, and then it will be very easy to determine the sign of the polynomial. So this is method 2, and now we will do the code for the same method. Now the code is pretty much the same that we have discussed in the method 2. So here we have this function main, in which we have taken input for n and q, and then we'll also define an array which will store our roots of the polynomial, which will be n number of roots. So we'll take input for that, and then we will sort them in descending order. So using greater and in the bracket int, we'll sort them in the descending order. Now after sorting them in descending order, we have defined x, which will be our queries, and we have defined a jump value which we took to be square root of n, right? Now we are running a while loop because we need to print the values for each of the queries, right? So we'll input each of the queries that will be there in x. The queried value will be there in x, and first of all the position will be 0. We'll be starting with position 0. Now you see a while loop here that we were just discussing, that along with the jump value. So there will be two conditions that we'll be checking, that position plus jump should be less than n, it should not exceed the range of number of roots that are there with us, and a of position plus jump should be greater than x. So this is the condition that we were discussing about, which will help us to optimize our solution more and more. So this jump will be performed. If these two values are true, then this jump will be performed and position will be incremented by a value of jump. Now the second while loop will help us determine the exact position at which the root value has become less than x. So that exact position we will come to find out by using this while loop. Now after we have determined that position, then we are just supposed to check first of all that if that particular position, the value at that particular position of the root is equal to x, that is the queried value, then in that case the position, the polynomial will give us 0 as the answer. So we'll print 0. Else if the position which will determine the number of roots of the polynomial which are greater than the queried value x. If it is even in number, then we'll print positive, because then the polynomial will give us a positive sign. Otherwise, we will print negative because the polynomial is going to give us a negative sign. So guys, this was the code. Now talking about the time complexity of this method. So first of all, we are sorting. So for sorting, the time complexity is going to be n into log n. There will be no change in this. Now for each query, we are performing some operations. So definitely order of q will be there. Now along with q, earlier we had log n because we were performing binary search. But here we are not performing binary search. Here we are making iterations up to square root n. So that is why instead of log n, it will be square root n here. So this will be our time complexity for each of the queries. Now, if we combine these time complexities, then our final time complexity will be n into log n plus q into under root of n. This will be our final time complexity if we use this method to solve our problem. So this method is also known as square root decomposition. If you don't know about this method, then you can read about it on the internet. I'll also provide a link in the description box. You can go check it out. So guys, that's it. Now we have solved this problem. If you also want to solve tougher problems, then you can check out the Unacademy app, where CodeChef teaches various things about competitive programming. And also, if you want, then you can take the plus subscription of Unacademy if you want to enhance your competitive programming. Also guys, if you have any problem or you have any other solution, then do not forget to post it in the comment section, and we'll discuss about it. We'll solve your doubts. You can also stay updated via our Telegram channel. The link is given in the description box below. So guys, please like the video, and I'll see you in the next one.